Hello, welcome to this lesson in AC circuit analysis. The title of this lesson is called Reactive Power with an Inductive Load. So we're going to talk about the concept of reactive power here, and we're going to be talking about the concept when that applies to having an inductor inside of the load. In the last section we had just a resistive network, just resistors, and we talked in great detail about what's going on with the power when we just have resistors. So if you haven't watched that section, go back and watch it, and to reacquaint yourself, what's happening with the resistive network is we have a non-zero average. We have an average amount of power delivered to that resistor, and it's oscillating, the instantaneous power is oscillating up and down, but it's always positive, and so there's always an average value when you have a resistive network. Here we'll talk about what happens when we have inductive loads. In the next section we'll talk about what happens when we have capacitive loads. I'm really excited to teach this because up until now we talk about resistors. Everyone can wrap their brain around resistors, right? Because resistors are kind of the easiest thing to understand in circuits. They obey Ohm's law, V is equal to IR, and you have some kind of familiarity with what's going to happen when these sinusoids go up and down and things are in phase. You know, the current and the voltage are in phase, so it's kind of, even though there was a lot of math in the last section, it was very easy to follow, I think, if you watch it enough times and study it enough times, what's really happening with a resistor. But when you have inductors and when you have capacitors, suddenly the current and the voltage across those things are no longer in phase, and things get a little bit murky. So we're going to take it slow. We're not going to do any problems. We're going to do theory for the next few sections, and when you get to your problems, you'll understand these terms. You'll understand what's really happening. So let's revisit. This is what I call the granddaddy power equation. I'm going to leave it on the board for a great many sections. It's instantaneous power. So if you start the stopwatch and time marches on, this is the time dependence here. This is a constant term. This is the time dependence. You stick in the numbers with your phase angles for the current and the voltage, which is going to be governed by your circuit that you have. And this is going to be some kind of sinusoid over time. And it's telling you that the instantaneous power is always changing. But we want to zero in on the case when we have just an inductive load. What's going to happen when there's just an inductor inside of the box? Last section we talked about what happens when there's a capacitor in the box. Now we're going to talk about if the load is purely inductive. What happens? And I can tell you right now, actually, it's something really cool that happens. And I find this stuff really fascinating with circuit analysis. So this is some of the reasons I'm really excited about teaching it. All right, the first thing you need to remember, there's very, very few things I tell you in circuit theory to just remember. Right? One of them is Ohm's law, V is equal to IR, right? You have to know that. Some of the real basic power equations, just memorize them. What I'm going to tell you here is something you should just remember. When you have a purely inductive load, all right, the current, okay, through that inductor lags the voltage by 90 degrees exactly. The current lags the voltage in an inductor or across an inductor by exactly 90 degrees. Current lags the voltage by 90 degrees. I'm going to show you how to prove that to yourself, but just remember it, because if you can just remember it, that these few little things I tell you to remember, it's going to make your life so much easier. So let's go down here and write that down, and I'll explain what I'm talking about. The current lags the voltage by, I'm going to put the word exactly, 90 degrees. And I'll give you a hint. When we get to capacitors, it's also going to be 90 degrees, but the current is not going to lag the voltage. In a capacitor, the current will lead the voltage by 90 degrees. So the 90 degrees part is going to be easy to remember. The leading versus the lagging is what always confused me when I learned this stuff the first time. Finally, you're just going to have to commit it to memory. The current lags the voltage in an inductive or across an inductive load when it's purely inductive.